We're going to continue with Electrochem today. Again, big idea 3, we're looking at electron transfer. We've talked about voltaic or galvanic cells. Ecell must be positive or negative for a voltaic cell. Positive. Therefore, making delta G negative, which indicates that the reaction is thermodynamically favorable. Okay, we won't get into voltaic cells until after break. Where we left off last time is right here. We had established, just to bring you up to speed, we know we're calculating the standard cell potential by doing cathode minus anode. And again, some of your review books will do it differently. Do whatever you want. Just make sure you're doing it correctly. If you don't want to change signs, this is the easiest way to go. We had said for a voltaic cell that E cell must be positive. Voltaic and galvanic would be synonymous terms. You can calculate delta G, the change in Gibbs free energy that determines thermodynamic favorability, by setting it equal to negative N, the number of moles of electrons, F, Faraday's constant, 96,485 coulombs per mole electron, times E cell. And if E cell is positive in a voltaic cell, then delta G must be negative, and therefore the reaction is thermodynamically favorable. So that's where we left off. Something we had talked about in our Thermo chapter, and again, you're seeing linkage between Thermo and Electrochem here. And you really want to think along those lines now, especially when you sit down and do your spring break assignment. You'll see that most of the Part 2 questions, if not all, do not assess a single concept. They're all combinatorial concepts. And you're seeing that Electrochem and Thermo are linking together here. So those are 2 chapters that you really want to go through together. And another thing, a few of the kids popped in and they're like, well, what should we do over break? And you have your spring break assignment. It's going to take you about 4 hours, not in one sitting if you don't have the time to do it that way. But also, why don't you start to really make a list of concepts you don't fully understand? If you want me to make a matrix for you, I can work on that later today. And maybe you can sit there and just check off, I don't really get this. I'm good at this, you know.
Do you think we should time ourselves for 4 hours? And then
Yeah, you'll see when you read the directions to the spring break assignment that part 1 is 90 minutes, and that is one 90-minute setting with no phone, no TV, no nonsense, just focus. And then the part 2, you'll need 105 minutes to sit through, and then you're also required to grade your part 2. You can either grade yours or have a little party with your friends and grade each other's. And honestly, that's the best exercise of all, is the grading of it. In any event, you've got thermodynamically favorable due to the negative delta G. We also had talked about the fact I left off my little not sign there. I was sloppy. We also had talked about earlier in the year how delta G is equal to negative R, R being 8.314 joules per mole Kelvin, times the temperature in Kelvin, ln of KEQ. We had talked about in the Thermo chapter, and now what we can do is we can set these 2 equations equal to one another. So we have RT ln of KEQ is equal to not negative because the negatives cancel, is equal to NFE. So I'm going to cancel those negatives. And we can set those 2 equal to one another. And then we can calculate E cell if we want. We've got RT ln of KEQ over NF. So that's a new derived formula not given in that regard. And I guess if you wanted to, you could calculate KEQ by doing E to the NF Ecell over RT. That'd be a bit much. I can't think of an instance where you would do that. But this is definitely utilized, not as much as it used to be because it's not a plug and chug situation so much anymore. But you could calculate Ecell in that regard. And as a reminder, something we had mentioned earlier in the year, remember, if you were going after KEQ from here, I could see it. KEQ is equal to E negative delta G, and that has to be in joules, over RT. That is an equation that you have seen and used previously, hopefully successfully. And you'll see that I scratched some of the information in your notes. In your notes, you actually can simplify that particular formula. They used to give it to you and they don't anymore. So we're not going to worry about it. Let's just have this, which we easily can derive. In the example provided, it says calculate values of delta G and KEQ at 25 degrees Celsius for the following reaction. Now previously we did this through delta H and delta S information. We could calculate delta G and then in turn calculate KEQ. The only difference here is we're going to do it from Ecell. So this reaction is provided to you. You can see that copper is being oxidized to copper 2+. So this equation would be flipped. And if this is actually oxidation, is that occurring at the cathode or the anode? Anode. So what is the anode? What metal? What metal is the anode? Copper. Good. And what metal represents the cathode? Silver. You've got it. Good. And we're going to be making little cells like that. So these reduction reactions and reduction potentials will be provided to you. You recognize this as oxidation here, the loss of 2 electrons at the anode, reduction at the cathode. We do cathode minus anode, and our E cell is 0.460 volts. To calculate delta G then, as we did the other day, it's negative NFE. Once the electrons are balanced, you have 2 here, you multiply by 2, you multiply by 2, you multiply by 2. You do not multiply by 2, as we talked about in intensive property. So 2 moles of electrons. Faraday, you can use 500 here or 485. It really makes no difference. And here's your E cell that you calculated. Here's your delta G in joules. This is a problem we've done before. You can put it in kilojoules if they ask you to. If not, leave it in joules, because to get to KEQ, you're going to need joules. So then the question becomes, well, why would anybody put it in KEQ, put it in kilojoules instead for delta G? If you had a combinatorial type question where you calculated delta G and you were given delta S, maybe you would be asked to calculate delta H in kilojoules per mole. So that's why sometimes you change your units. In any event, this is review back from your Thermo chapter. So once you have your delta G, you can manipulate this equation as shown. Don't forget the negative sign here. A negative times a negative is a positive, and this must be in joules or it won't cancel out with the joules in the R. Don't forget the temperature has to be in Kelvin. For those of you who do some practice problems, this will not be an issue. For those of you who decide to take the quiz cold, it could be. And KEQ is 3.6 times 10 to the 15th power. with that KEQ, is the forward or reverse reaction favored? Forward. KEQ is greater than 1, show forward equilibrium favorability. KEQ greater than 1, delta G must be negative. Shown here is another problem. I did it out for you, and then we'll take a look at that problem. It says calculate values of delta G and KEQ. We're trying to show this relationship between these variables.
Why do you use Celsius for delta G, but you use Kelvin for?
You don't. It's given to you in degrees Celsius, but you'll need Kelvin.
Oh, so you switch
Because if you did something in the lab, your thermometer would be in degrees Celsius. All right? Here's your reaction. Gold 3+ is being reduced or oxidized to gold. Has to be reduced because you would be gaining electrons. So reduction occurs at the cathode. The silver equation would be flipped around and multiplied by 3, but you're not going to change this. This is going to be at the anode. Cathode minus anode gives you this. Delta G, negative NFE, as we talked about the other day. Here is your delta G in joules. KEQ, and this you've seen before as well. Just watch the sign. You've got a negative times a negative is a positive. There's your KEQ value. Let's take a look at the problem and see if we can work it. I think you will be pleasantly surprised with how simple it is. It says calculate values of delta G and KEQ for a voltaic cell. As soon as you see voltaic cell, that tells you that Ecell must be positive, and that's the key to success right there. The only thing they give you are the reduction reactions. Remember, they're going to give you reduction reactions because reduction potentials are what would be listed on a table. So one of these equations is backward, and we need to figure out which one it is. It might also ask you to write the balanced equation, so we're going to do that as well. What's the only way to get a positive from these numbers? What minus what? This minus that, right? So this has to be reduction at the cathode, and this must be oxidation at the anode. Does that make sense? Because that's the key. Your E cell, you know, is the cathode minus the anode. And you know for a voltaic cell, this must be positive. The only way to get a positive is to do this minus this, because they're both negative. So you have negative 0.13 volts minus negative 0.74 volts. And that's equal to 0.61 volts. Good so far? And Andrew, that made sense once I said it again? Yes, yes? Okay, good. And then we want delta G, and that is equal to negative NFE. The N may not be grossly obvious to you. What's N? 6 is correct. 96,485 coulombs per mole electron. And again, In a multiple choice situation, I might do something like this because it'll be easier to play with. And we got our Ecell. Remember, moles of electrons cancel. Coulombs times volts is equal to joules. That's my delta G. And then my KEQ is equal to E negative delta G over RT. So E, we're going to have positive 350,000 divided by 8.314 joules per mole Kelvin times the temperature, which is 298. And we were in 2 sig figs as we went, and we'll keep it that way. And I have 2.2 times 10 to the 61st power. And for voltaic cell, KEQ will be greater than 1 because you have a thermodynamically favorable reaction. So you want to be able to get Ecell, as we talked about previously. You want to be able to calculate delta G, and now we want to be able to link it to KEQ. There's all kinds of fun stuff you can do with it. Now, one of the other things we said is that under standard conditions, we use that not sign. And that is when concentration of ions is 1 molar, or if you have a gas, the pressure is 1 atmosphere. But sometimes you're working under non-standard conditions where you have alterations in concentration, so less than or equal to 1 molar. No, less than or greater than 1 molar, or pressures that are not equal to 1 atmosphere. So under non-standard conditions, you won't have these. You'll have some variation. And this can be an extremely confusing concept that we will introduce here. I think you'll be good at it because you really grabbed Le Chatelier's principle and you can think of it that way, but you don't explain it that way, and we'll go through the pieces there. We want to look at the effect of concentration on cell voltage. Under standard conditions, the concentration is 1 molar. Is this an equilibrium reaction? No, because it only has the forward arrow. And Le Chatelier's principle does apply to equilibrium conditions and perturbations therein. So you can't use Le Chatelier's principle to explain what happens to voltage when you alter the concentration. Yet it is helpful when you think about it in your interpretation. So in a multiple choice situation, yeah, you're going to dive right in with it because it's going to work. In a part 2 situation, you need a little more explanation, and that's what we'll take a look at. If you increase the concentration of copper 2 ion, or you decrease the concentration of zinc ion, the forward reaction is favored. I didn't say equilibrium shifts in the forward direction because you don't have an equilibrium state. What you're actually seeing is the driving force on the electrons is favored, and as a result, if the driving force on the electrons are favored and the forward reaction is favored, Ecell is going to increase and delta G becomes more negative, or the reaction is more thermodynamically favorable. We'll look at it mathematically in a minute, which I actually prefer, but sometimes not the kids. If you decrease copper 2 ion or increase zinc 2 ion, a product, the reverse reaction will be favored, but the better way to state it is that the forward reaction will be opposed. When the forward reaction is opposed, Ecell decreases. You don't have this not sign anymore because you're not under standard conditions. You don't have 1 molar of ion. Ecell decreases and delta G becomes less negative. It doesn't necessarily become positive, but less negative. The way you actually explain this is through the Nernst equation. We used to use the Nernst equation to solve for different variables. You're not going to be solving for anything with the Nernst equation, and I hate to say it, the AP, if you look at your formula sheet, they don't give you the Nernst equation. What the Nernst equation does, and that Nernst equation is right here, is it relates cell voltage for non-standard conditions. So when you have non-standard conditions, you have Q. And it relates Ecell under non-standard conditions to Ecell under standard conditions, as well as concentration of reactants and products expressed through Q. And they don't give you this. They give you this. And through a series of steps, you can derive it. So they give you this, which we saw in the Thermo chapter, and this, which we saw in the Thermo chapter, this, which we've just been introduced to. You can set these equal to one another, and you can solve for Ecell very simply as we showed you initially. It will be RT ln of KEQ over NF. And all they're doing here is expanding upon it, and it is a little bit tricky. And initially, when we didn't see it provided, we thought that it was out of the curriculum, and then of course it appeared on the exam, much to our disliking. We know that delta G is equal to negative RT ln of KEQ is equal to negative NFE, cell under standard conditions. We have Ecell is equal to RT ln of KEQ over NF, correct? So what happens here is under non-standard conditions, this is equal to Ecell under standard conditions minus RT over NF, and now you have non-standard conditions, so you have ln of Q. And let's take a look at a few ln of q's. What's ln of 2? What's ln of 1? What's ln of a half or 0.5? The ln of a number greater than 1 is positive, correct? The ln of a fraction is? Now if you had ln of a quarter, and we're not even going to look at what it is because who cares? Is it going to be closer to 0 or farther from 0 than this in the negative number line? It would be more negative, right? We can write it in and take a look at it. But it's more negative, correct? And the ln of 4 then has to be this. That's a 3. And so that's more positive, if you will, than what you had for ln of 2. You don't have to know what ln of 2 is equal to. However, in a backward way, you actually have it. Because the half-life for a first order reaction is equal to 0.693 over K, and 0.693 is the ln of 2. In any event, if you're looking at ln of Q, and let's say that you have the equation that I gave you previously, what would Q be? What over what? Concentration of zinc 2 ion, or zinc ion has to have a 2 plus charge, over copper 2 ion. Correct? Say it again? Right, you got it. Now, if we increase copper, we said that the driving force on the electrons is favored, and as a result, Ecell will increase, correct? If we increase this concentration, this is 1, this has to be greater than 1. Q will be a fraction, correct? If Q is a fraction, ln of Q will be positive or negative? Negative. And if ln of Q is negative, you have Ecell minus a negative, so you're adding to this, and as a result, Ecell will increase, and I shouldn't have that little thing here. Bye-bye. Let's think of it a different way. Let's say that we increase the zinc. Now, the forward reaction is opposed. If we increase zinc, Q will be greater than 1, and the ln of a number greater than 1 will be positive. And now, if we put a positive in here, we're subtracting a larger number from Ecell under standard conditions, and Ecell under non-standard conditions will do what? Decrease. And that's got to be your explanation. And it's very, very tricky. Let's walk through one to make sure that we can do it. Years ago, you used to have to calculate Ecell under non-standard conditions when we altered the concentrations. You will not be asked to do that, so we're not going to do that example. This would be a problem that would be non-calculator based, although if you had a justification, it would be in part 2. Take a look at this problem. First thing we want to do, we've got a balanced equation. We are told initially that the concentrations of the ions are 1 molar, indicating standard conditions. In this case, it has been indicated that copper is being oxidized or reduced. Oxidized, and silver ion is being reduced. So, what's the cathode? What is it? Silver is correct. The cathode is silver. Does its mass increase or decrease as the reaction runs? It would increase because silver is being generated in the reaction. It is a product. How would you calculate Ecell? You would do cathode minus anode, so you would do 0.80 volts minus 0.34 volts is equal to 0.46 volts, correct? Now, here's the new piece. If silver concentration is increased, the value of Ecell under non-standard conditions will increase because the forward reaction is favored, and this is the phrase you're looking for. The driving force on the electrons is favored. In a multiple choice situation, when you favor the forward reaction, Ecell increases. Very straightforward. However, can you explain it in terms of the Nernst equation? So you've got copper plus 2 silver ion generating copper 2 plus 2 silver. You're increasing this. And again, you see, forward reaction. You know that Ecell under non-standard conditions increases. But in regard to your explanation, based on the Nernst equation, which they don't give you, you know that it's ln of copper 2 plus over silver ion squared. If you increase the silver ion concentration, ln of a fraction will be negative. As a result, you are adding to Ecell under standard conditions now, And as a result, Ecell under non-standard conditions increases. And that'll do it for you. And that's why I just mentioned those ln's. An ln of a fraction, that is an ln of a number less than 1, is negative. Concentration cells is no longer assessed, so we're not going to play there. pH measurement is no longer assessed. The pH meter is interesting. Batteries are interesting. Corrosion is interesting. I don't really see anything that's going to drive it in that direction. I'd skim through it because it's interesting. I would watch this video here because it'll link what we've done with what we're going to do. And when we come back from break, we'll do the last piece of the puzzle and we'll get some review in. You were provided with a practice quiz on this chapter. It's something you will want to look over break as well. You won't be quizzed the week you return because we have a very fun lab to do first. So you have a little wiggle room there. But when you come back, you want to make sure you understand voltaic cells, how to calculate Ecell, how to calculate delta G, K, EQ.